Humanity stands at a crossroads between planetary infancy and cosmic maturity. The key to this leap is becoming a Type 1 civilization, a society that commands the total energy of its home world. By the end of our journey, you will possess the complete blueprint of 30 specific technologies required to make that staggering transition a reality. We will uncover the tools to end scarcity, heal our planet, and reach for the stars. What does it truly take to manage an entire world? And could the first steps already be hidden in our labs today? The responsibility that comes with such power is immense. What kind of future would you choose to build with it? Our blueprint begins not on Earth, but with the star that gives us life. To command the energy of a world, you must first command the energy of its sun. The first technology on our list is a celestial architecture so vast it redefines the word power. We call it a Dyson Swarm. Forget the image of a solid, rigid shell. This is something far more dynamic and achievable. Imagine millions, then billions, of individual solar collectors, each one a vast, thin mirror or a sprawling panel, all flying in a careful, coordinated dance around our sun. They would form a loose, shimmering cloud, capturing sunlight not just on one side of a planet, but from nearly every angle of the star itself. This is not science fiction, but a logical, physical endpoint for any civilization whose appetite for energy outgrows its planetary surface. The visionary physicist Freeman Dyson, who framed this idea not as a blueprint but as a detectable signature of advanced life, saw it as an inevitable step. The energy harvested would be beyond comprehension. We measure global energy use today in terawatts. A full Dyson Swarm could provide yottawatts. That is a 1 followed by 24 zeros. It is the difference between sipping from a garden hose and redirecting the flow of an entire river. The challenges, of course, are titanic. It requires autonomous robotic factories in space, mining asteroids for material, and creating structures that can withstand solar winds and intense radiation for centuries. But the payoff transforms everything. With that much power, you could stabilize Earth's climate at will, power entire industries in space, and fuel the engines of starships. It marks the moment a civilization graduates from living on a world to operating its home star system. Yet harnessing a star's raw output is only the beginning. What good is a river of energy if you have no way to channel it, to send that power precisely where it is needed, across the vast emptiness of space? That river of stellar power needs a planetary artery to flow through. The second technology on our list is a global superconducting grid. Think of it not as a collection of power lines, but as the planet's central nervous system for energy. Today, our electrical grids are inefficient, losing a significant portion of their power as heat over long distances due to resistance in the wires. A superconducting grid solves this with a profound physical principle. By cooling special cables to incredibly low temperatures, often using liquid nitrogen, we can make electricity flow through them with virtually zero resistance. Zero loss. This means power generated by a solar farm in the Sahara could be sent directly to a factory in Shanghai, or energy from a North Sea wind farm could illuminate a home in Buenos Aires, all instantly and without waste. The implications are transformative for a world managing planetary-scale energy. It would end the concept of a localized blackout, as the grid would dynamically reroute power around any problem. It would make intermittent sources like wind and solar perfectly reliable, because when the sun isn't shining in one hemisphere, it's blazing in another, and the grid seamlessly balances the load. This turns energy from a scarce, localized commodity into a ubiquitous planetary utility, as dependable and accessible as the air we breathe. Building such a grid is a monumental engineering challenge. requiring advances in materials science to create practical, high-temperature superconductors and the deployment of a vast, interconnected network of cryogenic conduits across continents and under oceans. But its completion marks the moment a civilization truly wires its world into a single, efficient, and resilient entity. Yet, a network this vast and dynamic cannot be managed by human hands alone. It requires a governing intelligence, one that can make billions of adjustments per second to keep the entire system in perfect harmony. This vast, humming grid needs a mind to run it. The third foundational technology is a planetary-scale artificial intelligence. This is not a single supercomputer in a secret mountain base, but a distributed, networked consciousness woven into the very fabric of our global infrastructure. Think of it as the administrative and cognitive backbone of an entire civilization, a vast mind overseeing Earth's complex systems in real time. It would monitor climate patterns, global traffic flows, resource allocation, and energy distribution, making trillions of subtle optimizations every second to maintain a state of dynamic equilibrium. While today's artificial intelligence excels at narrow tasks, like recognizing images or playing a game, a planetary AI would represent a leap into superintelligence, a system capable of holistic understanding and management at a scale impossible for any human committee. Philosophers like Nick Bostrom have long pondered the profound implications of such an entity, not as a ruler but as the ultimate civil servant. Its functions would be staggeringly broad. It could prevent ecological tipping points by modeling entire biospheres and managing carbon cycles with surgical precision. It could orchestrate global logistics, ensuring food, water, and materials flow to where they are needed without waste or delay, ending scarcity at its root. The ethical and control frameworks for creating such an intelligence are arguably as critical as the technical code itself. How do you align its goals permanently with human flourishing? How do you ensure its decision-making is transparent and accountable? Answering these questions demands a level of global cooperation we have never before achieved. But if we succeed, this planetary mind liberates humanity from the burden of micromanaging a complex world. It handles the calculus of survival, freeing us to focus on creativity, exploration, and building the physical layer of our civilization anew. And that new layer begins with the most fundamental material of all, the substance we shape into our homes, our cities, and our future. But what if the very substance of our world was no longer fixed but fluid? The fourth technology on our blueprint shatters our deepest assumptions about physical reality. We are talking about programmable matter, often envisioned as something called utility fog. Picture a room filled not with air but with 1 trillion microscopic robots, each one smaller than a grain of sand, all working in concert. This is not a single object, but a dynamic, intelligent material that can change its form and function at a command. A wall in your home could become transparent to let in light, then reshape itself into a table, or dissolve entirely to open up space. A tool you need simply assembles itself from the surrounding fog, and when you are done, it disassembles back into invisible, waiting components. For a Type 1 civilization, this represents the ultimate mastery over the physical environment, rendering the very idea of material scarcity obsolete. Construction and manufacturing are transformed overnight. Instead of building a bridge, you would instruct the fog at the riverbank to coalesce into a bridge of perfect strength and shape, and later, you could tell it to redistribute itself for another purpose, leaving no waste behind. This utility fog could also act as a universal repair system, flowing into cracks in machinery or infrastructure and reconstituting the damaged structure at a molecular level. In daily life, it could provide perfect haptic feedback in virtual spaces, letting you feel the texture of a digital object as if it were real. The foundational research for this is happening today in labs focused on nanotechnology and distributed robotics, where scientists are learning how to make tiny machines communicate and cooperate. While still largely theoretical, the trajectory is clear. The implications touch every aspect of existence, turning our surroundings into an extension of our will, perfectly adaptable to any need or desire. It is the final step in dematerializing our needs, where objects are temporary events rather than permanent possessions. Yet, to command matter at this grand architectural scale, we must first learn to command it at the most fundamental level imaginable, atom by precise atom. The mastery of matter begins at the smallest scale imaginable. The fifth technology on our blueprint is molecular nanotechnology, the art and science of building things one atom at a time. This is not just making things smaller, it is about absolute precision. Think of the difference between piling lumber to build a house and being able to place every single splinter and nail in the exact perfect position for maximum strength and efficiency. That is the leap this technology represents. Visionaries like Eric Drexler outlined a future where we could have desktop devices, often called fabricators or molecular assemblers, that work like advanced three-dimensional printers but operating at the atomic level. You would provide a design file and a supply of basic feedstock atoms, perhaps from a jar of purified carbon, hydrogen, and other elements, and the assembler would precisely position these atoms to build the object from the ground up. The result would be a product with atomic perfection, no weak points, no impurities, and absolutely zero waste. For a civilization managing a planet, this is the ultimate tool for ending material scarcity. Need a new communication device? Assemble it from recycled plastic bottles and old electronics. Require a complex medicine? Synthesize it perfectly, molecule by molecule, in a home unit. Even food could be constructed from elemental components tailored for perfect nutrition. The medical implications are profound. Microscopic machines or nanobots could patrol our bloodstream, repairing damaged cells, clearing plaque from arteries, and eliminating pathogens the moment they appear. This could mean the end of most disease and a radical extension of healthy human life. Of course, such power requires immense responsibility. The same principles that allow for healing could, in a worst-case scenario, be misused. Scientists have long debated safeguards, including strict programming limits to prevent the hypothetical runaway replication of assemblers, a scenario sometimes called the gray goo problem. The path forward involves developing these technologies with layers of embedded safety, much like the rigorous protocols in advanced biology labs today. Mastering construction at this scale gives a civilization true abundance, freeing it from the constraints of traditional mining, manufacturing, and logistics. But what about the living systems of our world? Command over the inanimate must be matched by an equally profound understanding of life itself. The code of life is no longer a locked book, but an open text we are learning to edit. The sixth technology for a Type 1 civilization is advanced genetic engineering and directed evolution, a mastery over biology that transforms us from inhabitants of the biosphere to its conscious stewards. This begins with tools like CRISPR, a molecular scalpel that allows scientists to cut and paste genetic sequences with astonishing precision. But for a planetary civilization, this is just the first clumsy word in a new language. We are moving toward a future where we can not only repair flawed genes that cause illness, but rewrite entire genetic pathways to enhance resilience, adapt organisms to new roles, and guide the trajectory of life itself. Imagine crops engineered to thrive in salt-rich soil or arid deserts, ending food insecurity by turning barren land into fertile ground. Envision bacteria designed to digest plastic waste in our oceans or consume industrial pollutants in the air, acting as living cleanup crews for the planet. We could even see the carefully considered restoration of lost species, using genetic blueprints to bring back key organisms for ecosystems that have grown unbalanced. This power extends inward as well. The potential to enhance human health, extend our natural lifespan, and bolster our cognitive and physical resilience is written into this same code. Such possibilities carry an ethical weight as heavy as any physical structure we might build. They force us to ask fundamental questions about fairness, identity, and what it means to be human in an age where our own biology becomes a choice. Yet, if guided by wisdom and a profound sense of stewardship, this technology offers the ultimate path to harmonization. Instead of exploiting nature, we could learn to collaborate with it at the deepest level, designing living systems that produce fuels, build materials, and sustain environments in a seamless, sustainable loop. It represents the moment a civilization stops fearing the forces of biology and begins to conduct them. But to fuel a global society engaged in such vast projects, we must fundamentally reimagine the most basic human need, the very act of feeding ourselves. The next step in our blueprint moves from the abstract code of life to the tangible reality of a meal. The seventh technology is a complete reimagining of sustenance itself, closed-loop vertical farming and food synthesis. Envision city skylines where glass towers shimmer not with offices, but with verdant, layered fields of greens, fruits, and grains, stacked dozens of stories high. Inside, every variable is controlled. Perfect spectrums of light mimic the ideal sun. Nutrient-rich mist nourishes roots without soil, and every drop of water is captured, purified, and recirculated in a continuous loop. This is agriculture as a precise, predictable engineering science, liberated from the whims of weather, the invasion of pests, and the slow tragedy of soil depletion. Its yield per acre dwarfs any traditional farm, using a tiny fraction of the water and no chemical pesticides at all. But the revolution does not stop with plants. Alongside these towers, cellular agriculture facilities cultivate meat, not from animals, but from carefully nurtured cells, producing beef, chicken, or seafood that is biologically identical to the conventional kind, but without the environmental cost or ethical concerns of industrial farming. Beyond even this, advanced food synthesis could one day assemble perfect nutrients directly from elemental components, creating tailored foods for any dietary need or culinary desire. For a Type 1 civilization, this means the permanent end of food insecurity. Hunger and malnutrition become relics of a more precarious past. The implications ripple across the planet. Vast tracts of land currently used for grazing and monoculture farming can be returned to nature, allowing forests to regrow and grasslands to recover, creating massive natural engines for carbon sequestration and biodiversity. Food production becomes hyper-local, integrated into the urban fabric, eliminating the energy cost and fragility of global supply chains. This technology transforms our relationship with the biosphere from one of extraction to one of elegant, efficient integration. We cease to be hunters and gatherers on an industrial scale and become cultivators within a balanced planetary system. But a civilization nourished by such advanced means must also be sustained in health. The bounty of perfect food requires a parallel leap in our ability to care for the body it sustains. Health is no longer a fragile state to be defended, but a dynamic condition to be continuously optimized. The eighth technology on our blueprint is comprehensive personalized medicine and anti-aging therapies, a paradigm where healthcare ceases to be about fighting crises and becomes about sustaining peak human potential. This begins with a silent, internal sentinel network. Microscopic monitors built from our mastery of nanotechnology would flow through our bodies, analyzing blood chemistry, identifying precancerous cells, and neutralizing pathogens in real time, long before we ever feel unwell. Your personal health would be a constant, gentle stream of data to a protective system, not a mystery visited during a yearly checkup. This data merges with a deep reading of your unique genetic blueprint. Advanced gene therapies tailored precisely to your genome could correct inherited vulnerabilities, repair damaged DNA from environmental exposure, and recalibrate metabolic pathways to resist age-related decline. The most profound frontier lies in regenerative medicine. Imagine therapies that can instruct your own body to rebuild a damaged liver, regrow cartilage in joints, or even restore function to an injured spinal cord. Aging itself is reclassified from an inevitable decline to a collection of manageable biochemical processes, cellular repair mechanisms that can be reset, accumulated damage that can be cleared. The goal shifts decisively from merely extending lifespan to radically expanding health span, the period of life spent in full vitality. The societal implications of such a leap are as vast as the science. It would challenge our deepest structures, from pension systems and career paths to our philosophies of life's purpose. A civilization that masters this technology must also grapple with questions of equitable access and the psychological adaptation to a fundamentally new human timeline. This biomedical infrastructure would be deeply woven into the planetary artificial intelligence and the network of molecular assemblers, creating a seamless, invisible support system that maintains the physical vessel of its citizens. But a body sustained for centuries is only half the equation. To navigate a future of such complexity and longevity, the mind within must be equally resilient, adaptable, and enhanced. The mind is the final frontier within. The ninth technology for a Type 1 civilization is a direct bridge between thought and machine, advanced brain-computer interfaces, and cognitive augmentation. This is far more than a tool for controlling a robotic arm with a thought, though that is a powerful beginning. We are talking about a seamless, high-bandwidth connection that merges biological consciousness with the vast digital networks of a planetary intelligence. Imagine accessing a piece of information not by typing a query, but by simply wondering about it and having the answer appear in your mind with the clarity of a remembered fact. Envision communicating with another person not through words, but by sharing a pure concept, a feeling, or a sensory experience directly, with all its nuance intact. This technology would fundamentally rewire the human experience. Learning a new language or a complex scientific discipline could become a process of direct knowledge transfer, augmenting our natural memory and cognitive speed. Our very senses could be expanded to perceive data streams, quantum fields, or the gentle hum of the global energy grid as a new layer of reality. For a civilization managing planetary-scale systems, this symbiosis is not a luxury but a necessity. How else could a human mind hope to intuitively grasp the trillion data point model of the global climate, or collaborate with a planetary artificial intelligence in real time? It enables a true merging of intelligences where human intuition, creativity, and ethical reasoning are amplified by the vast processing power and memory of machine networks. This gives rise to the possibility of a collective human intelligence, a networked consciousness capable of solving problems no individual mind could ever untangle. The philosophical questions are as profound as the engineering challenges. If memories can be stored externally and experiences shared directly, what becomes of the concept of a single, isolated self? Neuroscientists and philosophers engage deeply with these questions, exploring how such tools might reshape our understanding of identity and shared experience. The cultural explosion would be unimaginable, birthing new forms of art, storytelling, and collaboration that we can scarcely dream of today. This neural link represents the ultimate interface, the final step in making the staggering complexity of a Type 1 civilization comprehensible and manageable to the human beings who guide it. Yet, a mind expanded to cosmic awareness will naturally yearn to reach beyond the confines of its biological body, to project its consciousness into the vast environments it seeks to understand and shape. A civilization of networked minds needs physical hands to shape the world. The 10th technology on our list brings that thought to life through humanoid robotics and general artificial intelligence avatars. These are not the clanking, single-purpose machines of an assembly line. They are dexterous, perceptive, and profoundly adaptable partners, designed to move through spaces built for human bodies, using tools made for human hands, but with a precision and endurance we could never match. Picture a surgeon of flawless steadiness performing a micro-scale operation from halfway across the globe, its every movement guided by a master physician through a seamless neural interface. Envision teams of such robots working in the radioactive heart of a fusion reactor, repairing components with gentle, exacting care, or constructing habitats in the vacuum of space, unfazed by the lethal environment. For a Type 1 civilization, these avatars become the indispensable physical extension of human will. They are the explorers who map the crushing depths of our ocean trenches, the first settlers who prepare the dusty plains of Mars, and the vigilant maintainers who keep the vast, invisible networks of our planetary infrastructure humming. This liberates humanity from dangerous, repetitive, or simply impossible labor, not by making people obsolete, but by elevating the entire species to a role of creative direction and supervisory wisdom. The true key to their potential lies not in their limbs but in their minds. These physical forms require a general artificial intelligence, an OGI, to animate them. Unlike today's narrow artificial intelligence, which excels at one task, a general intelligence would possess the flexible understanding and problem-solving ability of a human, able to learn a new skill, adapt to an unexpected obstacle, and make complex ethical judgments in the field. It is this cognitive leap that transforms a sophisticated tool into a true agent, capable of representing human interests and executing complex missions with genuine autonomy. The development of such an intelligence is perhaps the single greatest technical and philosophical challenge on our list, demanding breakthroughs in machine learning, cognitive architecture, and crucially, in creating systems whose goals are perfectly and permanently aligned with human flourishing. Once realized, these avatars, equipped with sensors that can see in spectra we cannot, and manipulators that can feel at a molecular level, will redefine the very concept of work. In a world of material and energy abundance, where robots handle production and maintenance, human activity naturally pivots toward exploration, art, scientific inquiry, and the deep, relational aspects of culture. The entire economic framework of society would transform around this new reality. But to create such sophisticated partners, we cannot rely on traditional factories. We need a new genesis for machines, a method of creation as fluid and intelligent as the robots themselves. The blueprint for a machine begins not on a factory floor, but within the silent logic of a design file. The 11th technology on our list is additive manufacturing at macro and micro scales, the flexible production engine of a Type 1 civilization. This is the art of building by adding rather than carving away, and its power lies in its breathtaking range. At one end of the spectrum, picture a construction site where a massive, gantry-mounted nozzle moves with patient grace, depositing layer upon layer of a specially formulated concrete or composite material. It does not construct a building, it prints it, room by room, with hollow spaces for wiring and plumbing already woven into the structure's very bones. This is contour crafting, a method that could create disaster-resistant homes in hours, not months, using locally sourced soil or recycled materials. At the same instant, in a clean room across the city, another type of printer is at work at the opposite extreme. It uses focused beams of energy or microscopic jets of fluid to assemble components not from bulk materials, but from individual particles, building up complex circuitry, medical implants, or even mechanical parts with atomic precision. This is manufacturing liberated from the constraints of molds, dyes, and subtractive cutting. It allows for the creation of objects with impossible geometries, lattice structures that are simultaneously incredibly strong and almost weightless, or cooling channels that wind like fractal rivers inside a rocket engine blade. For a planetary society, this means the death of the fragile, globe-spanning supply chain. A community needing a new water purification unit does not wait for a shipment from another continent. It downloads the design file and prints the device using local feedstock, perhaps even recycled plastic from its own waste streams. This democratizes the means of production, enabling local self-sufficiency in everything from basic tools to vital infrastructure. It synergizes perfectly with our earlier technologies, acting as the physical expression of programmable matter and the macroscopic outcome of molecular nanotechnology. The result is a world with near-zero material waste, where objects are created on demand for purpose, and where innovation is limited only by imagination, not by the tools available in a factory. Yet, to print a starship engine or a kilometer-high habitat, you need more than a sophisticated printer. You need the cosmic equivalent of a supermaterial, a substance that can withstand the dreams you intend to build with it. The very atoms of our future are waiting to be told what to become. The 12th technology on our blueprint is the conscious design of matter itself through metamaterials and smart materials. This is not about finding stronger steel or lighter aluminum. It is about writing the rules of physics into the architecture of a substance. Metamaterials are engineered with intricate patterns smaller than the wavelength of light or sound they are meant to control. By sculpting these nanoscale structures, we can dictate how energy moves through them in once impossible ways. We could create surfaces that render an object invisible by bending radar or light waves around it, not with magic but with geometry. We could design perfect lenses for telescopes that see further into the cosmos without distortion, or for communication devices that focus signals with absolute precision. For a Type 1 civilization, these are the essential components of grand projects. The individual satellites of a Dyson Swarm would be sheathed in metamaterial films to manage the star's brutal radiation and convert its light into usable energy with near-perfect efficiency. On Earth, buildings could be clad in smart materials that change their opacity to manage heat and light, or their texture to shed rain and snow, responding to the environment like a living skin. Smart materials take this a step further by adding a sense of awareness and reaction. Imagine a bridge made of a composite that senses a crack forming and instantly releases healing polymers to seal it. Think of an aircraft wing that changes its shape in flight to optimize aerodynamics, not with mechanical flaps, but because its very structure flexes and adapts to air pressure. The development of these substances represents a deep convergence of nanotechnology, quantum physics, and advanced simulation, where we model and then manifest behaviors once confined to theory. They become the silent, intelligent fabric of our civilization, from cloaking devices for exploration to sensors that can taste the chemical composition of the air. Yet, a cloak that bends light or a wing that morphs in flight requires immense, instantaneous power to function. The sophistication of our materials is meaningless without an equally sophisticated way to store and release the energy that animates them. Power is only as useful as your ability to hold it. The 13th technology on our blueprint is ultra-high-density energy storage, the silent reservoir that makes a dynamic civilization possible. Imagine a battery no larger than a suitcase, yet holding enough energy to fly a passenger jet from New York to Tokyo, or to power a small town through a week of stormy darkness. This is not about incremental improvements to today's lithium-ion cells, but a fundamental leap in our capacity to bottle lightning. The pathways are as elegant as they are varied. Solid-state batteries replace flammable liquid electrolytes with stable, solid materials, promising densities that rival gasoline itself. Graphene supercapacitors could charge in seconds and discharge in enormous bursts, handling the sudden demands of a city's power grid or a massive construction mesh. Even microscopic flywheels spinning frictionless in a vacuum could store energy as pure motion, ready to be converted back to electricity with near-perfect efficiency. For a Type 1 civilization, this technology is the indispensable buffer between generation and use. It solves the ancient, stubborn problem of intermittency. When the sun is hidden or the wind is still, the stored energy from a clear, windy day seamlessly takes over. It decouples consumption from immediate generation, making energy truly reliable and portable for the first time in history. This unlocks everything else on our list. Advanced robotics no longer need to tether to a power outlet, granting them true autonomy. Electric aviation becomes not just feasible, but superior, enabling silent, emission-free global travel. Off-grid habitats, whether in remote Earth locations or on the surface of Mars, can operate independently with vast, resilient power banks. With this puzzle piece in place, the entire concept of an energy grid transforms from a fragile delivery system into a robust, flexible network. Energy becomes a tangible asset you can carry, place, and deploy anywhere, turning every vehicle, every building, and every tool into a potential node in a planetary power web. Yet, storing energy is only one side of the equation. To build the structures that will house our civilization and reach for the stars, we need to move beyond traditional mining and processing, to source our materials not from the scarred crust of Earth, but from the boundless resources above it. Distance collapses when you can cross a continent in the time it takes to watch a film. The 14th technology on our blueprint is a planetary transit system of breathtaking speed and silence, Hyperloop and vacuum Maglev networks. These are not mere trains, but land-based spacecraft, capsules or pods that glide through low-pressure tubes at near supersonic speeds, or float frictionless above magnetic tracks in an evacuated tunnel. The principle is one of elegant reduction. By removing most of the air from the tube, you eliminate aerodynamic drag, the primary enemy of high-speed ground travel. The result is a system that moves people and cargo at over 700 miles per hour, using a fraction of the energy of a jet aircraft and with no direct carbon emissions. For a Type 1 civilization, these networks become the indispensable arteries of a connected world. Imagine departing from a station in London and arriving in Beijing for a morning meeting, or shipping a critical component from a factory in Texas to an assembly line in Singapore in under half a day. This level of connectivity dissolves the old economic and cultural barriers of geography, fostering a truly integrated global community. The engineering challenges are monumental, involving the construction of thousands of miles of precisely aligned, sealed tubes that can maintain a stable near vacuum, and the management of the immense forces required for acceleration and deceleration with passenger comfort and absolute safety. Yet the payoff reshapes civilization itself. It dramatically reduces the need for short-haul aviation and long-haul trucking, freeing skies and highways. It enables the rise of megaregions where cities hundreds of miles apart function as a single, continuous economic and social zone. Urban planning is transformed as the value of location is redefined not by proximity to a port or highway, but by proximity to a maglev portal. This restitching of the world's fabric makes the entire planet feel local, manageable, and intimately connected. But a civilization that has mastered crossing its own surface will find its ambitions pressing against the final frontier, the sky itself. The very efficiency of these ground-based systems highlights the next, more profound bottleneck, escaping the gravity well of our world to access the infinite resources above. The sky is not the limit, but a gateway we must learn to open daily. The 15th technology on our blueprint is the construction of permanent, high-capacity highways to the stars through space elevators and electromagnetic mass drivers. For a Type 1 civilization, the rocket equation is a prison. It demands that you carry an impossible mountain of fuel just to lift a pebble of payload into orbit, a cycle of staggering inefficiency that has kept humanity tethered to its cradle. The space elevator offers an elegant escape. Picture a ribbon, a tether of unimaginable strength, anchored to a platform on the equator and extending over 35,000 kilometers upward to a counterweight in space. Along this ribbon, electric climbers powered by lasers from the ground or solar panels would glide silently upward, carrying people and cargo into orbit for a fraction of today's cost. It is a bridge turning a violent, explosive ascent into a smooth railway journey into the sky. The primary obstacle is the tether itself. It must be stronger than any material we currently produce, likely woven from carbon nanotubes or advanced graphene fibers, capable of supporting its own colossal weight and the stresses of weather and orbital mechanics. While immense, this challenge is one of engineering, not fundamental physics. An alternative or complementary system is the electromagnetic mass driver. Imagine a miles-long track built on a high mountain slope or even on the lunar surface, using powerful magnetic fields to accelerate a payload capsule to escape velocity. It would launch silently without combustion, like a bullet from a railgun, sending raw materials from the moon or processed metals from asteroids on precise trajectories to orbital factories. Together, these systems shatter the economic barrier to space. They transform access from a rare, risky event into a routine, industrial process. The implications are as profound as the construction of the first transcontinental railroad or the Suez Canal. With cheap, bulk access to orbit, everything changes. We can construct vast orbital habitats, not cramped stations, but spacious settlements with artificial gravity. We can deploy the first true components of a Dyson Swarm, building the solar collectors that will power our civilization. Most critically, we can begin the systematic harvesting of near-Earth asteroids, those drifting mountains of pure iron, nickel, platinum, and water ice. This is the moment a civilization stops being planet-bound and becomes truly spacefaring, its economy and imagination expanding into the solar system. The resources of a single asteroid could supply all of Earth's industrial metal needs for centuries, ending destructive terrestrial mining. But to process those raw materials and build in the void, we cannot send up traditional factories. We need a new kind of industry, one born in the silence of space itself. The silent mountains drifting between worlds hold the keys to our cosmic future. The 16th technology on our blueprint is asteroid mining and in-situ resource utilization, the ultimate act of turning space itself into a workshop and a warehouse. These are not distant, abstract rocks, but treasure troves of pure potential. Imagine a small fleet of robotic craft, more like diligent bees than massive machines, arriving at a near-Earth asteroid. They anchor themselves to the dark, dusty surface and begin a precise, methodical disassembly. Using focused solar mirrors to heat and fracture rock, or mechanical processors to grind and sort, they extract the asteroid's raw wealth. Some asteroids, known as M-type, are essentially mountains of solid metal, rich in iron, nickel, cobalt, and platinum group elements. Others, the C-type asteroids, are carbonaceous and loaded with something even more precious, water ice, bound up in the clay-like minerals. This is the fundamental economic shift for a Type 1 civilization. Instead of laboriously lifting every gram of material from the bottom of Earth's deep gravity well, we learn to live off the cosmic land, using resources already floating in the zero-gravity environment where we need them. The applications are immediate and transformative. That harvested water ice is not just for drinking. When split by solar-powered electrolysis, it becomes liquid hydrogen and liquid oxygen, the most powerful chemical rocket propellants we know. This means we can establish fuel depots at strategic points in space, like Lagrange points, turning them into interplanetary gas stations. A spacecraft bound for Mars could launch from Earth with minimal fuel, refill its tanks in orbit, and journey onward with a full load, making missions far more efficient and frequent. The metals extracted become the literal building blocks of our expansion. In vast, automated orbital factories, these raw materials are fed into three-dimensional printers and assemblers, fabricating everything from the skeletal frames of space stations to the radiation shielding for habitats on the Moon. This in-situ resource utilization, or ISRU, is the principle of using what you find where you find it. It is what will allow us to build a permanent lunar base using lunar regolith for construction, or create radiation shelters on Mars from the red planet's own soil. The economic and environmental implications for Earth are profound. It offers a path to end destructive terrestrial mining for rare metals, preserving our planet's biosphere while providing a virtually limitless supply of materials for both planetary and orbital projects. This marks the definitive transition from a single-planet economy to a solar system-wide one. The wealth of an entire asteroid belt becomes accessible, funding not just exploration but the construction of wonders. Yet, raw materials alone do not build a civilization. To transform this cosmic ore into the architecture of our future, we require something more: a fully autonomous industrial ecosystem that operates in the silent void, building the world around us while we sleep. A silent factory orbits in the eternal night, lit only by the distant sun and the blue marble of Earth far below. This is the 17th technology, autonomous orbital shipyards, the industrial heart of a spacefaring civilization. Within these sprawling frameworks of girders and modules, there is no sound, no air, only the precise, unhurried ballet of robotic arms and focused energy beams. Here, spacecraft are not launched, they are born, using the steady stream of raw materials delivered by asteroid miners. Advanced three-dimensional printers and assemblers fabricate components in the perfect conditions of microgravity and vacuum. This environment allows for feats impossible on Earth. Imagine constructing a solar sail the size of a continent, its membrane gossamer thin and perfectly even, free from the sag of its own weight. Envision welding massive hull plates without the contamination of an atmosphere, creating bonds of flawless purity and strength. These shipyards enable the creation of vessels and habitats that could never survive the violence of a rocket launch from Earth's surface. A generation ship destined for another star, a rotating space colony providing artificial gravity for thousands, or the delicate, mirror-like segments of a Dyson Swarm, all must be built where they will operate, in the void itself. Managed by the distributed intelligence of the Planetary Artificial Intelligence and maintained by General Artificial Intelligence avatars, these facilities operate ceaselessly, an endless production line for humanity's expansion. With this capability, we move from merely visiting space to industrially occupying it. The ships built here will carry explorers to the moons of Jupiter and the rings of Saturn. The stations assembled will become research outposts, manufacturing hubs, and waypoints on an interplanetary highway. But to fill these magnificent structures with life, we must solve a more intimate challenge. A vessel is just a shell. To make it a home, we must learn to recreate within its metal walls the delicate, living bubble of a world. The air in your lungs and the water in your glass are part of a sacred closed loop. The 18th technology on our blueprint is the mastery of this loop on a grand scale, through closed ecology life support and the profound concept of terraforming. This begins with the life support systems for our first off-world homes. A habitat on Mars or a rotating colony in orbit cannot rely on shipments from Earth. It must be a miniature, self-sustaining world. Advanced systems will use a carefully balanced symphony of technology and biology. Genetically engineered plants, selected for high oxygen output and nutritional value, will scrub carbon dioxide from the air and provide food. Specialized bacteria will break down waste into usable nutrients for those plants, purifying water in the process. Every molecule of water, every breath of air is tracked, cleaned, and reintroduced, creating a perfect perpetual cycle. This is more than a machine. It is a living, breathing microbiosphere in a bottle, a testament to our understanding of ecology itself. It is the essential foundation for any permanent settlement beyond Earth, turning a hostile void into a place that can nurture human life indefinitely. This expertise in managing a world in miniature leads to the ultimate engineering project, terraforming. This is the deliberate, centuries-long process of altering an entire planet to make it more Earth-like. For Mars, the vision involves a sequence of colossal interventions. We might start by releasing trapped greenhouse gases from the polar ice caps, or manufacturing potent atmospheric compounds to thicken the thin Martian air, trapping solar heat to warm the frozen surface. Over generations, this could lead to liquid water flowing again in ancient riverbeds. The most ambitious proposals even consider restoring a protective magnetic field, perhaps by running enormous superconducting loops around the planet, to shield a future atmosphere and any life on the surface from solar radiation. While the timeline stretches beyond a single human lifetime, the technologies required are not magical. They are simply planetary-scale extensions of the climate management and geoengineering systems a Type 1 civilization must master to steward its own home world. Terraforming is the ultimate test of our role, moving from inhabitants of a planet to its conscious shapers, applying the lessons of Earth to awaken a dormant world. Yet, awakening new worlds also means accepting a sobering responsibility. A civilization that can gently coax life onto a dead planet must also be prepared to defend the fragile spark of that life from threats both cosmic and unforeseen. The silent, watchful eyes of a civilization must look outward as well as inward. The 19th technology on our blueprint is a comprehensive planetary defense and asteroid redirect system, a global immune system against cosmic threats. This is not about fear, but about fundamental responsibility. A Type 1 civilization has invested too much, has built too beautiful a world, to leave its survival to cosmic chance. The system begins with vigilance, a constellation of space-based telescopes and monitoring satellites with a single, clear mission: to map every sizable object in the inner solar system, calculating their orbits centuries into the future. This early warning network provides the most precious commodity of all, time. If a potentially hazardous asteroid is found to be on a collision course, we would have decades, not days, to respond. The response itself leverages our growing mastery of space. For a large, distant threat, we might deploy a kinetic impactor, a simple, high-speed spacecraft that smashes into the asteroid to nudge it ever so slightly off course. Over years, that tiny change in velocity adds up to a vast miss. For a smaller object or one requiring more finesse, a gravity tractor could be used, a spacecraft that simply flies alongside the asteroid, using its own minute gravitational pull to gently tug the rock onto a safer path over time. In more extreme scenarios, focused arrays of mirrors or lasers could vaporize a portion of the asteroid's surface, creating a natural jet of gas that acts as a rocket engine to push it away. This capability marks a profound shift in our cosmic role. We are no longer passive passengers on a rocky spaceship hurtling through a shooting gallery. We become active pilots, capable of adjusting our trajectory and safeguarding the future of all life on our world. It is the ultimate practical test of our spacefaring infrastructure, high-energy systems, and precision engineering. But the tools of defense can also become tools of creation. The same precise understanding of orbital mechanics that allows us to deflect a killer asteroid could let us gently guide a resource-rich one into a stable orbit around Earth or the Moon, turning a threat into a conveniently placed warehouse of precious materials. This conscious stewardship of our celestial neighborhood is the final signature of a mature planetary society. Yet, to orchestrate such delicate operations across millions of miles of empty space, and to manage the countless other systems of a global civilization, we require a universal language, a framework so clear and precise that machines, humans, and artificial intelligences can collaborate without a hint of misunderstanding. A civilization's thoughts must flow as freely as its energy. The 20th technology on our blueprint is a unified planetary information network, the silent, instantaneous nervous system that binds every other system together. This is far more than today's internet. It is a seamless, ultra-high bandwidth fabric connecting every person, every sensor in the global grid, every autonomous robot, and the planetary artificial intelligence itself into a single, coherent whole. Imagine a world where data moves with the effortless speed of a thought. A farmer in Argentina could access real-time soil moisture maps from a satellite constellation, cross-referenced with climate models from the planetary eye, to make perfect irrigation decisions. An engineer in orbit could feel the tactile feedback from a maintenance robot on the lunar surface through a lag-free connection, as if their own hands were there. This network enables the real-time symphony of a Type 1 civilization, where the energy grid, transportation flows, and resource allocation are all harmonized by the constant, flawless exchange of information. Its architecture would be a hybrid marvel, combining quantum-encrypted fiber optics for backbone security, global constellations of low-orbit satellites for universal coverage, and perhaps one day, experimental channels using neutrinos or quantum entanglement for truly instantaneous communication across vast distances. The result is the dissolution of information barriers, creating a shared, conscious understanding of our planetary state that every citizen can access and contribute to. It is the medium through which civilization-level decisions are informed, debated, and executed with transparency. Yet, a nervous system this vital cannot afford to be vulnerable. The integrity of every other technology depends on the absolute security of the information flowing through this network, a shield that must be unbreakable by any conceivable threat. The integrity of a civilization's mind depends on the secrecy of its thoughts. The 21st technology on our blueprint is quantum cryptography and unbreakable security, the ultimate lock for a world of open connections. In a society where brain-computer interfaces share private consciousness and the planetary artificial intelligence manages critical infrastructure, a conventional data breach is not a theft, it is a catastrophic failure of civilization itself. Quantum cryptography offers a defense rooted not in complex mathematics, but in the immutable laws of physics. It uses individual particles of light, photons, to create encryption keys. The act of measuring a quantum particle always changes its state, so any attempt to eavesdrop on the key exchange leaves an obvious, detectable disturbance. It is not that the code is hard to break, it is that the act of spying announces itself instantly. For a Type 1 civilization, this provides the foundational trust layer for everything. It secures the financial transactions of a post-scarcity economy, protects the sanctity of personal memory and communication shared across neural networks, and shields the core decision-making processes of the global artificial intelligence from sabotage. This technology transforms security from a software patch into a physical law, ensuring that the immense, interconnected power of a planetary society cannot be hijacked or destabilized by any conventional cyber attack. The early stages of this are being tested today in limited quantum key distribution networks, where banks and governments send data protected by photons. Scaling this to a planetary system is a monumental task of engineering, requiring a global network of quantum repeaters and satellites to distribute these fragile keys across continents and oceans. But its completion means that for the first time, absolute privacy and perfect trust become possible in a hyper-connected world. This strange, protective dance of photons reveals a deeper truth. The quantum realm is not just a shield for our information, it is a vast, untapped engine for processing it. The strangeness of the quantum world holds the key to unlocking nature's deepest blueprints. The 22nd technology on our blueprint is large-scale, fault-tolerant quantum computing, a new kind of thinking machine that does not simply calculate faster, but calculates differently. Where a classical computer uses bits that are either a 0 or a 1, a quantum computer uses qubits, which can be a 0, a 1, or a ghostly superposition of both states at once. This allows it to explore a vast landscape of possibilities simultaneously. The result is a tool of almost magical potency for specific, universe-scale problems. Imagine simulating the exact behavior of a new protein molecule to design a perfect cure for a disease, not through years of trial and error, but in a single afternoon of computation. Envision optimizing the entire global shipping network, every container ship, plane, and truck, to move goods with zero wasted fuel or time. Or picture cracking the enduring mysteries of high-temperature superconductivity or the conditions inside a fusion reactor, problems so complex they have defied our most powerful classical supercomputers for decades. For a Type 1 civilization, these are not academic exercises. They are the daily work of managing a planet and reaching beyond it. A large-scale quantum computer would work in seamless partnership with the classical planetary artificial intelligence, handing off the problems that require this unique form of processing. It would become the ultimate discovery engine, accelerating progress in every other field on our list, from designing metamaterials atom by atom to modeling the climate of Mars for future terraforming efforts. The monumental challenge is not just building such a computer, but keeping it stable. Qubits are incredibly fragile, easily losing their quantum state through the slightest interaction with the outside world, a problem called decoherence. Achieving fault tolerance means building systems with thousands of physical qubits working together to create a smaller number of perfectly stable logical qubits, all while housed in ultra-cold environments near absolute zero. It is a breathtaking feat of engineering and error correction. Yet, the prize is worth the pursuit. The insights generated would feed directly back into our fundamental understanding of reality itself, providing the raw data for our next great leap in perception. To test those grand theories of the cosmos, we will need eyes of unprecedented power and clarity, observatories that can see to the very edge of time and space. The cathedrals of science for a mature species are not built of stone, but of precision and ambition. The 23rd technology on our blueprint is next-generation particle accelerators and the pursuit of fundamental physics. To truly command the forces of nature, a civilization must first understand them at their most elemental level. This means building instruments of discovery on a staggering scale, particle colliders so vast they might encircle entire regions on Earth, or, to escape seismic and spatial limits entirely, be constructed in the silent expanse of space itself. These rings of power would accelerate particles to energies we can scarcely conceive, smashing them together to peer into the moments after the universe's birth. The questions they seek to answer are the deepest mysteries we know. What is the true nature of dark matter, the invisible scaffold of galaxies? What force drives the accelerating expansion of the cosmos we call dark energy? And is there a single, elegant framework that unifies all the fundamental forces of nature, from the glue of the atomic nucleus to the gravity that shapes the cosmos? For a Type 1 civilization, this is not abstract curiosity. It is strategic necessity. Every previous leap in technology, from the transistor to the laser, was born from a prior leap in pure scientific understanding. The insights gleaned from these cosmic microscopes could unlock entirely new principles of energy generation, perhaps tapping into the quantum vacuum or the fabric of space-time itself. They could reveal novel propulsion methods that make interstellar travel conceivable. The data torrent from these experiments would be a feast for our planetary artificial intelligence and quantum computers, creating a virtuous cycle where raw discovery fuels advanced simulation, which then designs the next, even more profound experiment. This commitment to foundational knowledge is the hallmark of a civilization thinking in centuries, not quarterly reports. It is an investment in the ultimate operating manual of reality. And one of the most profound chapters in that manual, waiting to be decoded, could teach us how to gently persuade gravity itself to bend to our will. Gravity is not a force to be overcome, but a language to be learned. The 24th technology on our blueprint is gravitational field manipulation and inertial dampening, a frontier that would redefine our relationship with the cosmos itself. While rooted in speculative physics today, the pursuit of this understanding is a logical destination for a civilization that commands a world. Imagine a spacecraft that does not fight gravity with explosive thrust, but simply steps over it, adjusting the curvature of space-time around itself to move in any direction without expelling reaction mass. This is the dream of reactionless propulsion, a concept that turns the immense distances between stars from an impassable barrier into a navigable highway. Closer to home, even partial control would transform daily life. The crushing forces of acceleration that limit how fast we can safely travel, whether in a car, a plane, or a rocket, could be gently negated by an inertial dampening field. High-speed trance, it would become as smooth and comfortable as sitting in a quiet room, opening the door to velocities that are currently lethal to the human body. The implications for construction are equally profound. Lifting massive structures would no longer require cranes of immense strength, but a localized adjustment of the gravitational constant, allowing us to move mountains of material with the precision of placing a feather. The theoretical pathways are as mind-bending as the applications. Scientists explore concepts rooted in general relativity, like the Alcubierre drive, which proposes contracting space-time in front of a vessel and expanding it behind, creating a warp bubble that moves faster than light without the vessel itself breaking local speed limits. Others investigate gravitomagnetism, a subtle effect predicted by Einstein's equations where a massive rotating object drags space-time around with it, wondering if this frame dragging could be amplified or harnessed. For a Type 1 civilization, investing in this long-term, foundational research is not a diversion but a core duty. It represents the ultimate ambition of physics, to move from observing the universe's rules to gently negotiating with them. Success here would mean graduating from passengers in a gravitational field to its conscious choreographers. Yet, while we dream of bending space-time itself, we must also build the engines that can carry us to the stars within the laws we currently understand. The bridge between our world and the next requires a fire sustained for years, even decades, in the endless dark. The journey between stars demands a fire that burns for generations. The 25th technology on our blueprint is advanced interstellar propulsion, the art of building bridges across light years. For a Type 1 civilization, this is the first tentative reach beyond its home star, a declaration that its future is not bound to a single point of light. The chemical rockets that served us so well within our solar system are useless here, their exhaust too slow to cross the unimaginable voids in any reasonable time. We must dream of new engines, picture a sail not of cloth, but of a mirrored film thinner than a soap bubble, stretching for kilometers. This is a light sail, and its wind is not air, but the focused beam of a colossal laser array stationed in orbit. Pushed by the pure pressure of photons, such a craft could accelerate to a significant fraction of light speed without carrying any fuel at all, a concept being tested in miniature by projects like Breakthrough Starshot, which aims to send tiny probes to our nearest stellar neighbor. For human-scale vessels, we look to the power of a star contained within a magnetic bottle, a fusion rocket. By fusing light atoms like deuterium and helium-3, it could generate a continuous, gentle thrust for years, cutting the travel time to the outer planets to months and making a journey to another star a multi-generational endeavor, but a possible one. More speculative, yet rooted in known physics, is the antimatter engine. When matter meets its antimatter opposite, they annihilate in a perfect conversion of mass to energy, the most potent reaction possible. Harnessing even a fraction of this power could propel a ship at velocities once confined to science fiction. And at the very edge of theory lies the warp drive, a concept that seeks not to push through space, but to contract the fabric of space-time in front of the ship and expand it behind, creating a bubble that moves faster than light without breaking the universal speed limit locally. While these latter concepts require breakthroughs in fundamental physics and energy generation far beyond our current grasp, their pursuit is essential. They represent the ultimate expression of a civilization's curiosity and its profound desire to ensure its legacy endures beyond the lifespan of its home star. Sending even a probe to another star is an act of faith spanning decades, a message in a bottle cast onto the cosmic ocean. It requires more than just a powerful engine. It demands a vessel that can sustain itself or its precious cargo in the absolute isolation of the interstellar deep. A human lifetime is too brief a candle for the journey between stars. The 26th technology on our blueprint addresses this fundamental mismatch of scales through suspended animation and extreme longevity for space travel. When a destination lies decades or even centuries away, we cannot ask explorers to spend their entire lives in transit, only to arrive old or for their great-great-grandchildren to complete a mission they never chose. The solution lies in mastering biostasis, the art of gently pausing biological time. Imagine a crew entering a state of profound metabolic suppression, a hibernation far deeper than any bear's winter sleep, induced by advanced pharmaceuticals or targeted cooling techniques that slow cellular processes to a near standstill. Their hearts would beat perhaps once an hour, their brains resting in a dreamless quiet, while automated systems maintain their fragile stasis and the ship glides silently on. Alternatively, the full realization of our earlier anti-aging therapies could extend health spans so radically that a 200-year voyage becomes a manageable portion of an active, conscious life, with crews remaining physically and mentally sharp for the entire duration. Both paths represent the ultimate mastery of human biology, turning it from a limiting factor into a flexible tool. The development of reliable biostasis is more than an engineering requirement. It is a profound philosophical step. It forces us to redefine the boundaries of life, consciousness, and consent, ensuring that any individual who steps into such a chamber does so with absolute understanding and trust in the systems that will one day awaken them. This technology bridges the impossible gap between the vast, cold distances of space and the warm, fleeting flicker of a human lifetime. It ensures that explorers do not merely arrive, but arrive ready, their bodies preserved, their minds intact, their mission still a living purpose. Yet, a ship coasting in the silent dark for generations is not an island. Even in hibernation or across the gulf of centuries for an awake crew, the need to connect, to send a whisper back home, remains a fundamental human impulse. For that, we will need a voice that can shout across light years. A whisper sent to the stars must carry across a gulf of silence so deep it defies ordinary understanding. The 27th technology on our blueprint is the creation of interstellar communication networks, a system of cosmic lighthouses and listening posts to connect our scattered future. The challenge here is not merely distance, but the brutal mathematics of signal decay. A radio transmission that leaves Earth as a focused shout becomes an indistinct background whisper by the time it reaches even the nearest star. To be heard or to listen across light years requires engineering on a staggering scale. We would need transmitters of immense power, perhaps powered by entire Dyson swarms, focusing their energy into laser-like beams aimed with celestial precision. On the receiving end, we might construct vast arrays of antennas spread across the quiet far side of the moon or floating in the depths of space, listening for the faintest echo of a reply. One elegant concept uses our own sun as a natural telescope. By positioning a receiver at the solar gravitational focus point, about 550 times farther out than Pluto, we could use the sun's gravity to bend and amplify signals from a specific star on the other side, creating a natural interstellar radio dish of unimaginable sensitivity. To ensure a continuous link, we might deploy a chain of autonomous relay probes along the route, each one catching a fading signal and boosting it onward, creating a stepping stone path of light across the darkness. For a civilization taking its first steps beyond its cradle, this network is its extended nervous system. It turns a daring, lonely expedition into a connected thread of awareness. The data flowing back would be priceless real-time sensor readings from probes orbiting alien worlds, atmospheric analyses from distant moons, and perhaps one day, the first tantalizing hints of complex patterns that are not of natural origin. This network does more than deliver information. It sustains the cultural and intellectual continuity of a species now living in more than one place. A child born on a world orbiting Alpha Centauri could hear the stories and songs of Earth as if they were broadcast yesterday, despite the 4-year journey of the light carrying them. It binds a scattered civilization into a single, conscious entity. Yet, the very act of building such a network forces upon us a profound and humbling responsibility. When you shine a beacon into the galactic dark, you must be prepared for what or who might see its light. As we extend our senses into the cosmos, we are also forced to look inward, to confront the ultimate questions of purpose, responsibility, and legacy that such power demands. Power demands wisdom as much as it does engineering brilliance. The 28th technology on our blueprint is not a machine or a material, but the social architecture that must contain them, global governance and ethical frameworks for technology. The tools we have explored, from planetary artificial intelligence to genetic rewriting, grant capabilities that could uplift or unravel our world. Their development cannot be a race without rules, nor can their benefits be hoarded by a privileged few. A Type 1 civilization must therefore weave a fabric of international cooperation as resilient and advanced as its power grid. This means treaties with real authority, governing the safe development of superintelligent systems, establishing fair protocols for modifying the human genome, and creating clear, equitable laws for using resources in space. It requires transparent frameworks for planetary-scale interventions, like climate engineering or asteroid deflection, ensuring such actions are taken with global consent and for the common good. This social technology must be adaptive, learning and evolving as our capabilities grow, always anchored in a core ethical commitment to the flourishing of all humanity and the integrity of Earth's biosphere. In this future, philosophers, ethicists, and diplomats hold a role as critical as any physicist or programmer, for they are the architects of the civilization's conscience. This framework is the essential check and balance, the system of guidance that ensures our immense power is wielded not with arrogance, but with profound foresight and a deep sense of stewardship. It transforms raw capability into civilized strength, and woven into this global conscience must be a humble, driving question: one that shapes our exploration and tempers our ambition. Are we alone? The search for an answer fundamentally defines our maturity as a cosmic species. The silence of the cosmos is not empty, it is a question waiting to be answered. The 29th technology on our blueprint is the active search for other minds and their creations, through programs like the search for extraterrestrial intelligence and the new science of artifact archaeology. For a Type 1 civilization, this is not a hobby but a fundamental act of self-discovery. It begins with listening, but it evolves into looking with a far more discerning eye. We would move beyond simply scanning for radio signals and begin to actively sift through the torrent of astronomical data for signatures of intelligence that are not broadcasts but buildings. Our most powerful telescopes, both on Earth and in orbit, would be tasked with a new kind of survey, hunting for evidence of cosmic-scale engineering. They would look for the distinctive infrared glow of a Dyson Swarm, a star shining oddly dim in visible light but radiating the waste heat of a civilization's industry. They would analyze the light curves of distant stars for the unnatural, geometric dips caused by massive orbiting structures. We would even train our nascent gravitational wave detectors to sense the vibrations of impossible engines or the wake of vessels moving at relativistic speeds. This search is a mirror held up to our own ambitions. In looking for the artifacts of others, we are essentially searching for our own future, for the possible endpoints of a technological path we have just begun to walk. Finding even a single relic, a silent probe drifting between the stars or the ruins of a megastructure around a long-dead star, would be the most profound discovery in human history. It would tell us we are not alone, that intelligence and ambition can survive the great filter of cosmic time. It would provide a living library of advanced physics and engineering, a treasure trove of knowledge gifted across the light years. Conversely, confirming a profound and enduring solitude would be equally transformative. It would place upon our shoulders a staggering and lonely responsibility, the duty to be the first, to be the ones who kindle the flame of complex consciousness in a dark and quiet galaxy. This dual possibility shapes everything from our philosophy to our long-term survival strategy. The very act of looking refines our own technology, teaching us what is detectable and perhaps what to avoid if we wish to remain unseen. It forces us to consider what we are building and what legacy, intentional or not, our civilization will one day leave etched into the light of our star. This reflection on legacy brings us to the final and perhaps most introspective piece of the puzzle. The final act of a mature civilization is not just to build but to remember. The 30th and culminating technology on our blueprint is the creation of a planetary and cultural memory archive, a fail-safe for the soul of our species. This is not a simple data backup but a sacred trust, a vault designed to outlast continents and survive any conceivable catastrophe, from a planet-wide natural disaster to the distant, cooling death of our own sun. Imagine this archive not hidden on Earth, where it remains vulnerable, but placed in the ultimate cold storage of the solar system, perhaps within the permanently shadowed craters of the lunar poles, or in a stable, self-maintaining orbit far from planetary debris. Its contents would be the sum total of who we are, a comprehensive library of human knowledge, from the foundational texts of every culture to the complete scientific understanding of our era. It would hold our art, our music, the stories that defined us, and the raw, unedited data of our history. Crucially, it would also preserve the biological blueprint of Earth's biosphere, storing the genetic sequences of millions of species, including our own, as a potential key to restoration. The medium itself must be as timeless as its mission. We might inscribe this knowledge onto ultra-durable physical substrates, like synthetic sapphire disks etched with femtosecond lasers, or crystals that store data in 5 dimensions, capable of surviving for millions of years without degradation. Alternatively, the archive could be a self-repairing digital system, maintained by autonomous robotic custodians powered by eternal solar panels, silently curating and copying the data across successive storage mediums as technology evolves. This endeavor is the ultimate expression of a civilization's self-awareness. It acknowledges our own potential fragility, even amidst immense power, and chooses to fight the entropy of forgetting. It is a message cast in two directions, inward to our own possible future and outward to the cosmos. For our distant descendants recovering from a dark age or rediscovering their origins after an epoch of change, this archive would be a lifeline, a Rosetta Stone to their own past. For any other intelligence that might one day find it, long after we are gone, it is our testimony. It says we were here, we wondered, we built, we felt, and we reached for the stars. This act of preservation brings our journey full circle. We began by learning to harness the energy of a star, the ultimate physical resource. We end by committing to safeguard the story of the beings who learned to do it, the ultimate cultural resource. It is the final, sobering, and beautiful responsibility of a Type 1 civilization to ensure that light, both from our sun and from our collective mind, is never completely extinguished. This intricate web of capabilities is more than a collection of tools. It is a living, breathing system. Each breakthrough we have explored does not stand alone, but rather interlinks with the others in a dance of mutual acceleration. The planetary artificial intelligence requires the vast energy of a Dyson Swarm to power its calculations, and in turn, its quantum computing cores design the metamaterials that make the swarm's components more efficient. Those same materials are forged by molecular assemblers, which are supplied by asteroid miners, whose operations are coordinated by the very artificial intelligence that started the chain. This is not a linear path, but a rising spiral of co-development, where a leap in one field sends ripples of possibility through all the others. The fusion of genetic engineering, closed-loop agriculture, and advanced medicine doesn't just solve individual problems, it weaves a new foundation for human health and environmental balance. The mastery of gravity and propulsion is meaningless without the life support systems to sustain the journey, and those systems are perfected through insights from nanotechnology and quantum simulation. This profound interdependence reveals the true nature of the challenge. Building a Type 1 civilization is less like checking items off a list and more like conducting a symphony of disciplines, each instrument essential to the harmony of the whole. Yet the most advanced symphony is silent without a conductor and a shared score. The technological tapestry we have described cannot emerge from competition or isolation. It requires a parallel and equally advanced social architecture, the glue of global cooperation, adaptive ethical governance, and profound cultural adaptation. These are the intangible technologies that allow the tangible ones to serve a unified purpose rather than fracture our world. The goal, therefore, shifts into clearer focus. We are not merely engineering new devices, but facilitating a fundamental transformation of the human condition itself. It is a transition from beings shaped by our environment to beings who consciously, responsibly, and gracefully shape our destiny within it. This integrated vision reframes every tool, from the mightiest stellar engine to the smallest medical nanobot, as part of a single great project, the maturation of a species and the thoughtful stewardship of its home in the cosmos. This blueprint is not a prophecy, but a profound invitation. The journey to a Type 1 civilization represents the greatest project humanity could ever undertake, a multi-century endeavor that redefines our very identity. We would transition from being children of Earth, shaped by its limits, to becoming conscious stewards of an entire star system. The 30 technologies we have walked through are not isolated gadgets. they are the essential stepping stones across that vast and turbulent river of possibility. Together, they weave a vision of a future where scarcity is a forgotten myth, where health and understanding are deepened beyond our current dreams, and where the horizon stretches from the ocean floor to the light of other suns. This is a future of radical abundance, longevity, knowledge, and expanded being. Yet, this dazzling potential carries a weight equal to its promise. Each tool demands from us a counterpart in wisdom. The power to reshape genes requires an ethical framework of profound compassion and equity. The intelligence to manage a planet necessitates governance built on transparency and global trust. The energy to move worlds must be paired with the maturity to use it gently. This path is not guaranteed by the laws of physics. It is made possible by the choices of human hearts and minds. It is a blueprint we must consciously, collectively, and courageously choose to build. As we stand here at the dawn of this potential age, we are presented with a defining question. Will we harness these converging tools to craft a civilization of shared prosperity, boundless curiosity, and cosmic stewardship? Or will we allow old divisions and short-term thinking to fracture this fragile ascent? The vision is clear, the components are falling into place, and the work, the most important work in our history, begins in this very moment. If this exploration of our possible future has ignited your imagination, consider subscribing. We will be diving deep into each of these revolutionary technologies in the coming videos, examining the science already in motion and the hurdles we must overcome. And we would love to hear from you. Which of these 30 steps are you most eager to see become a reality? Share your thoughts in the comments below.